In this video, we are going to see a very important concept of you know the pinch, right? And how pinch affects the heat exchanger network design. So let us try to understand the significance of pinch point, which we have arrived at in problem table analysis. So one thing is for sure that at pinch point there is no energy transfer, right? And we come to the pinch point, right? And that is the most constrained region of heat exchanger network. So basically it divides the process into two zones above the pinch with respect to the temperature. So if your pinch point is 60 and the temperature of the stream is 80, then it is above the pinch. If the temperature of the stream is 40, then it is below the pinch. So above the pinch and below the pinch two process zones are with respect to the temperature. Above pinch region is the one where process is in balance with minimum hot utility, because we provide the hot utility, and as the hot utility transfers from one interval to other interval, and as it reaches the pinch point, the amount of exchange becomes zero. So the entire process is in balance with the hot utility. If there is little change in the hot utility, it will be directly impacting the pinch point. So heat is received from hot utility and no heat is rejected, right? And hence this is a heat sink. So it receives it will never give away the heat to any other process or to the other region. Below pinch region is completely the extreme of the above pinch region, where its process is in balance with the cold utility. It means it gives away or it rejects the heat which is excess to that particular portion of the region of particular region of the process, and it is in balance with that. So here the process act as a heat source. So above pinch process is heat sink, it receives the energy. Below pinch process it heat source and it gives away the energy. And this decides that which kind of utility is to be supplied where. Naturally, hot utility is to be supplied above pinch, cold utility is to be supplied below pinch, right? Once we have obtained the pinch point, right, and we try to find the heat exchanger networking, place the heat exchanger networking diagram, right, we will see that a particular stream may be partially above pinch and partially below pinch. So all the streams which are below pinch will be taken to pinch point, and from pinch point to their final destination. So this we'll discuss when we discuss about problem pinch design method and applying that to heat exchanger networking. And as I already told in the beginning of this video, that pinch is the most constrained region where the delta T is 10, and if the temperature goes below that, then if this temperature difference goes below, then our entire energy balance get impacted, because our entire energy target is based on making sure that the delta T minimum condition is not violated. So this is something which happens, that this is your delta T minimum, this is below pinch, this is above pinch with respect to temperature, and this is your pinch point, right? So this is one region, this is another region. The same has been represented here in this form. The above pinch is in balance with this QH minimum, so this is heat sink, and below pinch is in the balance with QC minimum, so it is heat source, right? Correct. There is no heat flow between above pinch and below pinch region, as I already mentioned that at from pinch point there is no heat transfer. However, can I transfer heat from one zone to another zone thermodynamically? Is it possible? And if it is possible, whether it is beneficial or not is what we are going to see. So it's not that the flow is not possible, but if we exchange the heat between above pinch and below pinch, will it going to be beneficial or not is what we are going to see next. So let us try to understand that we are transferring some alpha amount of energy from above pinch to below pinch. Now above pinch is heat sink, so basically it requires the energy, and what are we doing is we are removing the energy from above pinch to below pinch. So when I supply it to below pinch it is source, so actually it should be able to reject, but it is receiving. So on both the sides, above pinch, which requires to be which requires heat, I'm removing heat from that, and below pinch, which wants to remove heat, I'm supplying it to it. The consequences of that is very clear, and that is the heat which I'm passing on alpha unit, that will be the deficit here in QH minimum. So you have to supply additional alpha unit to QH minimum. Heat which is supplied to below pinch region is addition to QC minimum, and hence you require additional alpha unit of cold utility. So basically what happens, that when you transfer some amount, XP amount or alpha amount, right, actually you add the same amount of hot utility and same amount of cold utility. So if I am exchanging X amount between top to bottom, above pinch region to below pinch region, I'll get a penalty of 2 times that X. Naturally the value may change, like naturally the quality of the utility may change, but if X amount is exchanged above pinch to below pinch, then I have to pay for 2x time the utility hot and cold, right? And hence process to process transfer across the pinch is not a feasible or a viable option. Now this is above pinch to below pinch, right? So this is something which I can do. Thermodynamically, it is possible to exchange heat above to below, because then the temperature difference is more than delta T minimum. But can I exchange the heat from below pinch to above pinch? This is something which we want, isn't it? We want this to act as a source and this to act as a sink. So can I exchange energy below pinch to above pinch? If I can do that, right, what will happen if thermodynamic allows? Then this will become QC minimum minus alpha and QH minimum minus alpha. So can I do that? Let us try to see that. So if I try to do this, that is below pinch to above pinch. Now what happens? This is your hot stream and this is your cold stream. Now below pinch the temperature is this, above pinch the temperature of cold stream is this. Now this temperature of hot stream is below the temperature of cold stream above pinch, and hence thermodynamically I cannot transfer the pinch. So there are two ways possible of transferring heat across the pinch, either from above pinch to below pinch. So above pinch to below pinch is feasible because the temperature difference is high. So this is hot stream, this is cold stream, so I can do that thermodynamically, but it's not practically viable because it is increasing the amount of utility. As far as utility is concerned, I want to transfer the heat from below pinch to above pinch, but in that case thermodynamics is not allowing me because the temperature difference is reverse, and hence transferring heat across the pinch is not uh, you know uh, it's not possible in a way, and that is why we say that the net transfer of heat across the pinch is zero. Correct? So this is something which we have to make sure. And in the same line, what we can understand is that if I add a cold utility above pinch, so if say for example I'm not transferring from above to below, but I'm supplying cold utility above pinch, it means what? I'm removing some amount of energy from the above pinch region. The moment I remove that energy, I need to supply that to I need to add that to minimum hot utility. So if I supply cold utility above pinch, then also I am adding that to the requirement of QH minimum. And if I am supplying hot utility below pinch, then also I am adding the requirement of energy. This is because we already said that above pinch the heat is the region is sink, and below pinch it is source. So below pinch there is no point supplying hot utility, above pinch there is no point supplying cold utility. So this tells you some basic rules of heat exchanger networking. No process to process heat transfer across the pinch, and that's why we design heat exchanger network separately for above pinch and to the below pinch. All the streams will come to pinch point and then from pinch point to their source or target temperature. Appropriate use of utility: hot utility should be always used above pinch, cold utility should be always used below pinch. These rules are both necessary and sufficient to ensure that the energy target is achieved properly. So our energy balance is tight and we achieve the energy target if we follow these rules. Providing that the initialization rule is adhered to, that no individual heat exchanger should have a temperature difference smaller than delta T minimum, which I already said. If you want to maintain delta T minimum and if you are following that, then these two rules are necessary and sufficient. So when we meet next time, we'll talk about certain process constraints. So we have said PTA, we said that energy targets are there, but then there are some process constraints which come across the designer before it implements the heat exchanger networking. So we'll discuss about those process constraints, and then we'll discuss about pinch design method or heat exchanger networking. Thank you.